Hello and welcome to this IChemE Global Awards 2021 webinar. My name is Mara Kefalopoulou and I'm your host for today's presentations. The IChemE Global Awards celebrate chemical process and biochemical engineering excellence and are widely considered as the world's most prestigious chemical engineering awards. Today we will be revealing the winner of the IChemE Oil and Gas Award, sponsored by the chemical engineer. This award recognizes the best project, process or product to demonstrate chemical engineering excellence in the oil and gas sector. Our awards judging panel has been working hard in recent weeks to review and rank all of the entries, and here are our finalists. A joint entry from the Non-Metallic Innovation Center, Saudi Aramco and TWI, 2 entries from Saudi Aramco, a joint entry from Saudi Aramco and King Fahd University of Petroleum and Minerals, University College London, and winners of the IChemE Malaysia Oil and Gas Award, Petronas Penapisan. 5 of our finalists joined us today to tell us more about the work and answer your questions. You can get in touch throughout today's webinar using the GoToWebinar questions box on screen. So let's get started with our first finalist, representing the joint entry from the Non-Metallic Innovation Center, Saudi Aramco and TWI. It's Rachel Lund, and we will start with a pre-recorded video.
Hi, my name is Rachel Lund and I work in the Numerical Modelling and Optimisation team at TWI. Today I'm going to talk about a body of work we've undertaken regarding the development of a framework to assess the risk of electrostatic discharge, or ESD, in polymer composite pipes used in the gas industry. This work was undertaken on behalf of the Non-Metallic Innovation Centre in collaboration with Saudi Aramco, and I'd like to mention my colleagues Tyler London and Michael Roy from TWI, and Abdurazak Tradia, Abdullah Sharani, Kostas Patopoulos, and Anwar Parvez from Saudi Aramco, who have greatly contributed to this work. So I'll start with some background on electrostatic discharge. There are 2 competing processes which determine the level of static charge accumulation on a pipe containing fluid flow: the rate at which charges separate and the rate at which charges recombine. Charge generation in flowing liquids is often described in terms of a double layer, as you can see in the top image. At the fluid pipe interface, one sign of charge is preferentially absorbed onto the surface of the pipe. As the fluid then flows, charge separation occurs. Although the charge is separated at the wall, turbulent flow mixes the charge into the bulk of the flowing liquid, creating a current known as the streaming current. The streaming current is equal to the volume flow rate multiplied by the fluid charge density. According to the National Fire and Protection Agency, a negligible amount of static electricity is generated in a single-phase gas flow. However, the presence of suspended solids or liquids results in charge carried by the gas phase, as can be seen in the bottom image. Liquid droplets tend to be charged due to the presence of a double layer and are not in electrical continuity, inhibiting charge relaxation. This is why a mist flow is undesirable in terms of electrostatic discharge. Competing with charge generation is charge recombination via dissipation pathways. Whilst the rate of charge generation is similar in both metallic and non-metallic pipes, the rate of charge dissipation is much lower in non-metallic pipes due to the higher resistivity of the non-metallic material. So when the potential difference between the inner and outer surfaces of the pipe reaches a critical level, discharge may occur. This can create large amounts of heat, resulting in melting and pinhole formation, as can be seen in the image on the right of the slide. This critical level is known as the material's dielectric strength, which is the maximum electric field that the material can withstand without breakdown. So the risk of electrostatic discharge should therefore be properly quantified and mitigated to ensure safe operation of non-metallic pipes in gas service, and this is a challenge that we've addressed in this work. Our aims were to develop a model of a non-metallic system, and this would be a multi-physics modelling approach to assess the risk of electrostatic discharge. The problem is highly nonlinear and multi-physical, and we would validate the model against experiment. So that was a challenge. So can we predict the risk of electrostatic discharge in non-metallic pipes? We created a hierarchical assessment method, whereby increasingly more detailed and complex models, as you progressed down the levels, gave more accurate results. So going into detail on the different levels. So our level 1 approach, which was the baseline approach that we adopted, and was the most conservative method and relied on determination of the flow regime using Baker or Mannheim charts, which use the gas and liquid velocity as inputs. If a missed flow was present, then it was determined that there would be a high risk of static charge buildup and potential discharge. And so the operating conditions would be altered to avoid this missed flow regime. This approach has several limitations, however, in that it is reliant wholly on the flow regime, it's overly conservative, and the proposed mitigation measures can be difficult to implement. In addition, it doesn't quantify the risk of ESD. Our level 2 approach aimed to address these limitations and improve the accuracy of the level 1 by quantifying the risk of electrostatic discharge. So the pipe flow module in console was used to calculate the gas velocity along the pipe, which is one of the main inputs into the Walmsley equation. The Walmsley equation was the analytical equation that we used to calculate the potential evolved at steady state on the inner surface of the pipe wall due to the streaming current, and is the equation shown to the left of the slide. The graphs are examples of the electric field across the pipe wall along the pipe. So the electric field is shown in blue and the dielectric strength of the pipe material is shown in orange in this case. The graph to the right of the slide shows a case where the risk is deemed low, so the maximum electric field is below the dielectric strength of the pipe. The graph at the bottom of the page shows the case where the electric field across the pipe wall is predicted to exceed the dielectric strength of the material, and so there is deemed to be a risk of electrostatic discharge in this case. Should this occur, a level 3 assessment will be undertaken to further remove conservatism. So limitations of the level 2 approach are that there are conservative assumptions incorporated in the Walmsley equation, such as the assumption of a constant electric field through the thickness of the pipe. In addition, the level 2 approach does not incorporate the charging effect due to the impact of the sand particles of any sand particles present, and it's challenging to compare different mitigation methods. So our level 3 approach was the full numerical modelling approach, accounting for the multi-physical behaviour in COMSOL. The velocity of the gas flowing through the pipe was found using the pipe flow module, and this was then used to calculate the streaming current expected along the pipe. An axisymmetric model in the AC/DC module was then used to calculate the potential on the inner surface of the pipe and the electric field across the pipe wall. The streaming current was applied as a boundary condition on the inner surface of the pipe, assuming exponential charge generation and charge relaxation, and grounding on the outer pipe surface and the pipe ends due to the buried nature of the pipes that we were modelling. The top image shows a close-up of the results of the plot of the potential from the AC/DC module. It's a close-up at the end of the pipe, and you can just about distinguish between the fluid and the pipe wall at the bottom of the top image. We then compared the results of the AC/DC module to the analytical Walmsley equation. We found that applying the streaming current using the external current density boundary condition, a specific boundary condition in the AC/DC module, whereby the electric field across the pipe wall was constant, provided results which coincided with the Walmsley equation, shown by the light blue and yellow lines in the graph. Applying the streaming current using the boundary current condition, which is more representative of the physical situation, allowed for a radially varying electric field that reduced the conservatism further and provided a more accurate value of the potential on the inner surface of the pipe. We then built upon the level 3 model to add in the behaviour of sand. We did this using the capacitor model, which was used to model the charge transferred during the impact by treating the sand and pipe as either side of a capacitor. Several tuning parameters in this model, so we used literature to tune that model. Then considered how to incorporate the charge transferred by the sand particles into the model, and we did this by effectively smearing out the localized charging due to the impacts over the impact area, whether that is the entire inner surface of the pipe for a fully suspended flow, or just the bottom region of the pipe for a moving bed. This was then incorporated into the model using an additional current density. So finally, we had a go at validating our models using a lab scale setup. We use a transient model in the AC/DC module this time because the steady state condition was not close to being reached, and compared this to charge evolved on a HDPE pipe in the lab. You can see in the graph to the left of the slide how the potential on the outer surface of the pipe was predicted by the model to increase with time, and the central graph shows how the experimental results. The model can be seen to be quite conservative compared to the experimental results, which is a positive starting place for us. However, it did not capture the skewed shape of the experimental profile, nor the correct magnitude, so more work needs to be done in this area to further investigate this. So, conclusions. Assessing and controlling the risk of electrostatic discharge facilitates the widespread use of non-metallic pipes in the oil and gas industry. Hierarchical modelling approach has been developed to assess at the design stage the potential risk of electrostatic discharge in non-metallic pipes. The Level 3 approach has the flexibility to assess the efficacy of potential mitigation methods, and our experimental validation showed the models to be conservative, although more work needs to be done to investigate the level of conservatism between the experiment and the model. So we aim to do some future work looking at validating the streaming current equation used in the models, and also the capacitor model, which incorporates the charging due to the sand. So thank you very much for listening. My name is Rachel Lund, and if you have any questions, please let me know. Thank you.
Rachel Lund joins us to answer your questions on our first presentation. So if you haven't already done so, now it's the time to get in touch via the questions box. And whilst I give you a moment on that, don't forget there are more IChemE Award webinars coming up this week. You can find the dates and times by visiting IChemE.org Global Awards. I don't see any questions, so thank you very much for getting things started, Rachel, with your presentation. It's now
no problem.
Thank you. It's now time to move on to our second finalist. Next up from Saudi Aramco, it's Fawaz Al-Sahan.
Thank you, Mara. Assalamu alaikum and greetings, everyone. My name is Fawaz Al-Sahan. On behalf of Saudi Aramco team, Omar Zaid, Fawaz Al-Hadlag, and myself, I would like to present to you our innovation, Smart Dewatering System. I will start with an introduction on tank dewatering. Then I'll describe the first component of Smart Dewatering System, the sound velocity dewatering system. I will describe next the second component, the multi-layer flow and level visualizer. The Smart Dewatering System setup and operation and advantages will be described. Then I will end my presentation with a few important points. Why we need automatic dewatering? Basically, we need automatic dewatering to address known challenges in the oil and gas industry. Mitigating the hydrocarbon drainage, basically to ensure only water is drained. To eliminate water overflow and prevent upset to downstream plant operation. To mitigate corrosion of the tank bottom plates. To eliminate manual dewatering, which requires many plant operators and a lot of time. To minimize manual water interface measurement and the need for the plant operators to climb the tanks and take this measurement. Here is the solution to address the highlighted challenges. The Smart Dewatering System. It consists of two components, the sound velocity dewatering system and the multi-layer flow and level visualizer. Allow me to elaborate on the first component, which is the sound velocity dewatering system. Sound velocity dewatering system consists of a smart sound velocity sensor, which can be intrusive or non-intrusive, a control system and an automatic control valve. The sound velocity dewatering system is a patented technology with built-in analytics, providing 3 parameters: the drain flow, the media recognition, and the drain valve status. So basically, it will indicate whether the valve is healthy, is stuck, or it has internal leakage. The system can be easily adopted, especially the non-intrusive type, and it will provide an automatic dewatering system. As each fluid has a recognized sound velocity, the sound velocity dewatering system will measure that sound velocity. Then it will recognize the type of media flowing in the drain pipe. Once definitely the drain valve is open and the drainage cycle is started. The system was deployed in Saudi Aramco. The slide showing one drain cycle. When the drain cycle starts, the drain valve basically opens and the water is drained. When the sound velocity drops below a preset value, the valve will be automatically closed. What you see in the slide is data collected from the first pilot that was installed. This slide is showing the first complete deployment of the sound velocity dewatering system back in 2010. You can see this in the screen, the non-intrusive sensors, the sound velocity sensors clamp on the pipe, the control valve, and the transmitter. The multi-layer flow and level visualizer is the second component. The multi-flow and level visualizer consists of an array of sound velocity sensors. It could be also another type of sensors. The multi-layer flow and level visualizer is a granted patent technology which provides 3 parameters: the total level, the water interface, and the temperature measurement. It's worth highlighting that the multi-layer flow and level visualizer scope goes beyond the tank dewatering and includes even interface measurement in the very challenges application in the upstream industry. The multi-layer flow and level visualizers can be made of ultrasonic sensors, as I highlighted. A simple setup is a couple also of pressure sensors at different heights, or basically an electromagnetic signals through a probe. The picture shows some installations during the evaluation of the technology. Using pressure measurement setup, for example, the accuracy was measured and found to match the manual interface measurement. The graph illustrated on the top. Also, the total level measurement is matching, which is basically the graph on the bottom of the screen. Let's now combine the 2 components together to build the smart dewatering system. The smart dewatering system is a filed patent. Within 2 months, it will be a granted patent because we just recently got the approval. It will provide up to 7 parameters: the total level, the interface, the fluid temperature, the hydrostatic pressure, the flow measurement, the drain media recognition, and also an important information, which is the drain valve analytics. Again, whether the valve is healthy, passing, or stuck. All of this data can be transmitted into the control room. The smart dewatering system was put in operation in June 2021, with the results meeting the expectation. The slide is reflecting the system in operation with specific parameters monitored. You can see the valve opening, the sound velocity measurement, and the interface level measurement. The smart dewatering system provides many advantages to the oil and gas industry. It improves safety by ensuring 0 hydrocarbon drainage to oily water sewer. It supports health, so no more manual drainage and interface measurement by the field operators. Smart dewatering is an IR 4.0 enabler built with smart sensors and uses data analytics. It addresses the crude quality and hydrocarbon losses in the oil industry. It prevents water overflow to the downstream unit in the refinery and to customers. It has a cost optimization when compared to other conventional solutions. It's a simple design which can be adopted in the running hydrocarbon tanks. which is exactly what we did. Smart dewatering journey started in 2010 with the first pilot and the first patent filing. Smart dewatering has 3 associated patents and wins many awards from Saudi Arabia, the King Award, from Saudi Aramco, from the Gulf Engineering Union Award, and the international awards like ISA Excellence in Innovation Award. We are also honored to be in IChemE 2021 finalist for 2 categories, the process automation and digitalization, and also for the oil and gas. To conclude, let me highlight a few points. Smart dewatering system is a digital transformation technology with 3 associated patents. It supports safety, environment, and health. Smart dewatering system supports recycle economy and net zero by eliminating hydrocarbon losses and emissions. Smart dewatering provides a simple and a cost-effective solution for automatic water drainage and monitoring the drain valve condition. Before I end, I would like to thank the Institution of Chemical Engineers for listing our innovation, the smart dewatering system, as a finalist in 2 categories, process automation and digitalization, and also for today's webinar, the oil and gas. This is truly an honor for us. Also, thank you for the opportunity provided to us, Omar Zaid, Fawaz Al-Hadlag, and myself, Fawaz Sahan, to present our innovation to the great audience joining us today. Thank you so much.
Thank you very much for that presentation, Fawaz. Once again, it's time for your questions. So if you want to get in touch and haven't already, now it's the time. And whilst we wait, the winner of this award will have the chance to lift the second prize before the end of the week. All of our team award winners qualify as finalists for our top prize, the Outstanding Achievement in Chemical and Process Engineering Award. And we will be announcing the winner of that award on Friday. We don't appear to have any questions, so thank you very much, Fawaz. And we're going to move on to our third presentation of the day. Once again from Saudi Aramco, please welcome Sanil Kokal.
Webcam. There we go. Okay, good day, everyone. And thank you, IChemE, for this event and for shortlisting our project as a finalist. It's exciting to be here. My name is Sunil Kokal, and I am a principal scientist in Expect Advanced Research Center in the Reservoir Engineering Technology Division, and a focus area champion for enhanced oil recovery, CO2, and sustainability. This project, CCUS and CO2-EUR demonstration project, is part of the company's Circular Carbon Economy Initiative, a framework and a holistic approach to reduce our carbon footprint and carbon emissions. CCUS, as you all know, will be an important part of the global climate change and how to provide solutions to that challenge. And I would like to emphasize at this point that the oil and gas industry is very well positioned to address CCUS because we have been the custodian of the reservoir where from the CO2 and the hydrocarbon came from, and we know how to deal with subsurface issues. So let me start with the project overview of this project. It's the first CCUS and CO2 enhanced oil recovery in the Middle East, and one of the largest in the Middle East and North Africa region. It captures up to about 800,000 tons of CO2 per annum and pipes it about 85 kilometers to the injection site. The CO2 injection started in mid-2015 and it's been about 6 years since we started injection. So we have had great success that I'm going to share now in the coming slides. Okay, so there are two major components for this project. The surface, which includes the CO2 capture, dehydration and compression facility, and also the pipe that takes from the capture facility down to the pilot area, and the subsurface, which is including of the injection and production facilities. And we have 4 injectors, 4 producers, and 2 observation wells that were drilled specifically for this project. And the wells are all equipped with downhole sensors, real-time measurement devices, and automatic valves. So we can get almost real-time data from this project. The project has become a test bed for the deployment of what we call Generation 2 intelligent field. And the timeline at the bottom of the slide shows the time it has taken for us to do this demonstration project. We started in 2006. We started production in 2012, and CO2 injection started in 2015. And today, on this day of 2021, it has been 15 years from the start of the project. And that emphasizes the time that these kind of CCUS projects take in terms of the conception, the design, the implementation, and the performance evaluation. And this slide shows exactly that. The green is the oil rate. The red dots is the amount of CO2 injected, and the yellow is the gas produced. And at the top, the blue dots are what we call water cut, or the amount of water that is produced. So you can see that before the CO2 injection started, sometime in middle of 2015, oil rates were dropping, and then after the CO2 injection started, they ramped up, and they have been producing at 3 to 4 times the base rate, what we call with the water cut. The important thing to note here is that we have injected so far 48 billion standard cubic feet of CO2. Of that, 20 billion standard cubic feet has been produced, and therefore the CO2 that is sequestered or stored or left behind in the reservoir is about 28 billion standard cubic feet, which correlates to 1.5 million tons of CO2. Now, this is a solid number, and this is the amount of CO2 that we have sequestered as part of this project. And as we expand, that number will increase. So in terms of impact, the 2 objectives that we had was to have some enhanced oil recovery, and those gains have been very positive. The recovery has been significant. And on the second objective of CO2 storage, 28 billion or 1.5 million tons of CO2 have been sequestered. And we are still working on it. The project is still going on. We are right now in the process of assessing and evaluating the whole project. By the numbers, this was the first CCS project in the greater Middle East region, highlighting our environmental stewardship and leadership. The 4x is the response from the project in terms of oil production. 59, 60% of the CO2 that we have injected has been retained in the reservoir. So that bodes very well for sequestration. And we are injecting up to 2,000 tons of CO2 every single day, which is equivalent to 170,000 cars being taken off the road. So it's really a win-win project, a win for the environment and a win for additional oil recovery. 17 million hours is the number of construction and operational man hours without any major incident for this project. And this project has received 10 prestigious international awards. In terms of HSE, we have addressed all aspects of health, safety, and environment, and each stage, and we continue to do that, and that is a driving force for this project. We spent a lot of time, effort, and resources in terms of monitoring to see where the CO2 is going. And in terms of measurement, we did measure everything that is going in and everything that is being produced. So injection and production rates, and from there, a material balance will tell you the amount of CO2 sequestered. We had deployed many technologies to look at the CO2 migration within the reservoir. An important aspect, to see how the CO2 is moving within the reservoir, called plume monitoring. Another aspect of this project was the oil saturation monitoring as to how this is desaturating the oil reservoirs. So in terms of lessons learned, we have learned a lot. The first one definitely is that you require a solid team. A multidisciplinary, multi-department team is required for a project like this. We have now created a knowledge base, both in terms of CO2 recovery and in terms of sequestration. We have developed our capability in many areas, including simulation, drilling, processing, injection. The point here is that you cannot decide today to inject CO2 and tomorrow you have a well executed project. It takes time. We have addressed a lot of operational issues, and like any new project, there will be headaches, and we have looked at those headaches, prescribed the Panadols or the Tylenol for it, and in terms of sequestration, a lot of experience has been gained. And in my books, one of the most important thing is the personnel that has been trained across the entire upstream, rather than across the entire company. And in terms of carbon footprint, there has been a huge reduction, and it has been a successful pilot. In terms of project KPIs, like I said, production gains have been positive. CO2 storage has been 28 billion SCF, and it has received 10 international awards. And the bottom row shows number of granted patents, patent disclosures, conference papers, journal papers, and the deployed technologies. So in my last slide, I would like to summarize that the project has been very positive, and we have met our objectives in terms of both sequestration of CO2 as well as in enhancing oil recovery. This has led to a huge reduction of carbon footprint given the size and scope of this project. And we have gained a lot of knowledge and experience on sequestration aspects. And in terms of monitoring and surveillance technologies, we have done some firsts in the world, some firsts in the Middle East, and some firsts within the company. Lots of lessons learned. We know that CO2 works, especially in terms of CO2 EURs, and you can sequester in a well-planned CO2 EUR project. We have addressed a lot of operational issues. We have developed capability building, and this has been an exemplary project, recipient of several awards. And it has been an important part of the circular carbon economy and energy sustainability within the company. So this last slide shows you a journey through the pictures. The CO2 compressor that you see is a massive undertaking. A huge facility is required just for the compressor. And my last comment would be that a project like this cannot be executed by one person. There's a team across the entire company, and I would like to acknowledge the contributions of each and every person who has worked on this project. Thank you very much.
Thank you very much, Anil. And we will pause now for Q&A. We have actually a couple of questions.
Sure.
The first one, interesting presentation. Could you please share some operational issues that you and your team managed to identify and resolve?
Okay, so let me start with the first issue that we had was the measurement of production rates using multi-phase flow meter. And we have spent a lot of time and effort in terms of addressing the multi-phase flow meter issues. We had, given that this is deployed in very mature part of the field, the water cuts are very high. In fact, the water cuts were 97, 98, 99% in the wells. Measuring the oil rate is a challenge. So we went through many iterations, and part of the reason I have lost some of my hair is because of solving that problem. Many others I can go on, but I will limit it to that for the time being.
Thank you. The other question we have is what percentage uptime have you managed to achieve with a CCS plant?
What percent? What, sorry?
What percentage uptime have you managed to achieve with a CCS plant?
Okay, so this is a very, very good question. And, the way it happens in life is that you design for a certain amount of CO2 to be injected. So that is the design value. Then there is the actual value of how much CO2 you are capable of injecting. And the third issue is really how much you have injected. So to answer the question, I would say about 75 to 80% is the time that the project has been, the plant has been online. Sometimes it can go down. It depends on a number of factors. It depends on, this plant is associated with another plant. So if that plant is shut down, this plant goes with it. And similarly, where you're injecting, if there's an issue in one of the wells or if there's an issue in the processing facility downstream, then this plant has to be shut down again. So to answer your question, about 75%, I would say, is a fair estimate of the time that the project is on.
Thank you very much. We don't appear to have any more questions, so thank you very much, Sanil. And let's move on. Unfortunately, our last two presenters didn't make it to attend this webinar, so we have reached now the time that we've been all waiting for. It's time to find out the winner of the IChemE Oil and Gas Award, sponsored by the chemical engineer. Before we do that, I'd like to thank all our finalists for joining us today and for taking the time to share more details about the fine work. I'm sure you will all agree it's a fine diverse range of work on show. Let's start by announcing our highly commended entries, and they are University College London and Petronas Penapisan. And now it's time to announce the award winner. Ladies and gentlemen, the winner of the IChemE Oil and Gas Award, sponsored by the chemical engineer, is Saudi Aramco. Congratulations to the Saudi Aramco team. Sanil, I hope you're still with us. If we can get you back on the screen, how does it feel to be an IChemE Award winner?
Thank you very much. And like I said in my last bit, that a project like this really requires a lot of teamwork. Many people helped from the inception to where it is today. And I would like to dedicate this award to each and every person who contributed to this award. And I think we have made a significant difference in terms of sequestration. And this is just the beginning. And the work will continue as into the next decade as Saudi Aramco and the oil and gas industry work towards decarbonization through CCUS and other technologies. Thank you very much.
Well, congratulations once again. And thank you to everyone for joining us today, especially all our finalists. We have still more IChemE Awards to come coming up the next days. We'll be back this afternoon to announce the winner of our Team of the Year award, but that's all for now. Thanks everyone for joining. Thank you very much.
Thank you.